Hello guys, welcome to my channel Maths 4747. In this video I am going to discuss some examples of vector spaces. So let's start with first example, that is Fn over F. So this is the field and this is your vector space. This F can be set of real numbers or complex numbers. So here I am going to discuss set of real numbers only. So we take this one vector space over R. So your field is what? Set of real numbers. Now our scalars are from this set of real numbers. So to show that Rn over R is a vector space. To show that, what we have to do, we have to prove all the 8 properties. So let's start with closure of addition and scalar multiplication. So guys, what is the closure property? Normally what we have to take some u and v, two elements from Rn, and we have to show u plus v also belongs to Rn, and if there is some u belongs to Rn and some a belongs to field, then we have to show AU product scalar multiplication belongs to Rn. So let's start with this. If U belongs to Rn, that means U is of n length vector. So you can write U as some A1, A2 and so on An, and your V is of the form, suppose V1, V2 and so on, V n length vector. Now if we add these two, U plus V, we get, there is a addition component wise. So A1 plus B1, comma A2 plus B2 and so on An plus Bn. If this A1 belongs to set of real numbers, B1 belongs to real numbers, then their addition also belongs to real numbers. So these components belongs to real numbers. That means this n tuple belongs to Rn. So my first property is satisfied, that is closure with respect to addition. Now second one, that is AU. AU is A into U is A1, A2 and so on An. Now multiply with respect to components. So this is A1, A2 and so on An. Now if A1 belongs to real numbers, then A into A1 also belongs to real numbers. If we multiply any scalar with this real number, then we get some real number. So this belongs to real number, this belongs to real numbers, and this whole and tuple belongs to Rn, which means scalar multiplication property is also satisfied. Now these two are the conditions for vector space, and the following 8 properties must satisfy. The first one, commutative addition, that is if u and v belongs to Rn, then we have to show that u plus v is equal to v plus u. Then we start with left hand side, that is u plus v. U plus v is a1 plus b1, a2 plus b2 and so on an plus bn. Now we can write, as a1 and b1 belongs to real numbers, so we can write this as b1 plus a1, or this thing as b2 plus a2 and so on bn plus an. So this is what? This is v plus u. So my first property is satisfied. Now second one is associativity with respect to addition. So in that second property, what we have to show, if there is some u v w belongs to Rn, then we have to verify u plus v plus w must be equal to u plus v plus w. So let's start with left hand side, that is u plus v. So first of all we have to find out this. This is what? a1 plus b1, a2 plus b2 and so on an plus bn. This plus w. W is some c1, c2 and cn. Now we can write this as a1 plus b1 plus c1, component wise addition. comma A2 plus B2 plus C2 and so on, AN plus BN plus Cn. Now we can write this as A1 plus B1 plus C1, and this is A2 plus B2 plus C2 because these are real numbers and associativity is bold in this case. So we can write this as Bn plus Cn. So this is what? This A1 and this. So you can write this as A1, A2 and so on, An plus B1 plus C1, B2 plus C2 and Bn plus Cn. This is U and this is V plus W. So we start with this and prove this. So that means second condition is also verified. Now third one, that is additive identity. So third one is if your U is of this type and identity 0. Identity element in Rn is of n tuple vector. So 0 is like 0, 0 and 0 n times. So if we add U plus 0, that is A1, A2 and so on An plus 0, 0, 0. Now we can add component wise this one A2 plus 0 and so on An plus 0. If we add any real number with 0, we get A1, A2 and so on An. This is your U. So now third property is also verified. Now fourth one, that is multiplicative identity. So for each element U in Rn, what we have to prove? 1 into U is U. So as you know that this is scalar 1 and 1 belongs to real numbers. So if we multiply 1 with A1, A2 and so on An, this is equal to 1 into A1, 1 into A2 and so on 1 into An. 1 into A1 is A1, A2 and so on An, and this is your U. So we started with 1 into U and we get U. That means this property is also satisfied. Now let's continue with the fifth one. So your fifth one is if there are some scalars like A and B belongs to field and there is some U belongs to Rn, then we have to show AB into U is equal to A into BU. So again with left hand side, AB, U is A1, A2 and so on An. Now multiply this with, so we can write AB, A1, AB, A2 and so on AB, An. Now we can write this as A outside and B A1, A outside B A2 and so on A outside B An. Now collectively we can write this as A into BA1, BA2 and BAN, and this can be written as A into BU. So basically this property is also satisfied. Now next one, all properties are similar, just you have to follow one procedure only. So sixth one, that is if A is any element from R and U and V belongs to Rn, then what we have to show? AU plus V is equal to AU plus AV. So A into U plus V, that is U plus V is A1 plus B1, A2 plus B2 and so on An plus Bn. This is equal to, we can multiply A with this, A into A1 plus B1, A into A2 plus B2 and so on A into An plus Bn. This one. So now we have to show this thing. So we can multiply A1, A B1, A A2 plus A B2 and so on A An, A Bn. So now we can separate A1, A2 and so on, AAN plus AB1, AB2, then ABN. Now we can take A outside, A1, A2, AN, A outside, B1, B2 and BN. So this is your U and this is your V. So now this property is also satisfied. Now last one is if there are A and B belongs to R field and U belongs to Rn, then you have to show A plus B into U is equal to AU plus BU. So again start with left hand side, that is A plus B. U means A1, A2 and so on, AN. That is equal to, we can multiply with this, A plus B A1, A plus B A2 and so on, A plus B AN. So now we can separate, that is A1 plus B A1, A2 plus B A2, AN plus B AN. Now we can separate A1, A2 and AAN. We are doing this because we have to prove this part. That's why we are doing this. So BA2, sorry, there is comma. So BA1, BA2 and BAN. Now we can take A common, A1, A2 remaining part, and now we can take B common from here. So A1, A2 and AN. This is A into U and this is B into U. So the last property is also verified. Now we can say that your Rn over R is a vector space with standard operations. So this is your first example. Now we can discuss some more examples. Second one, the set of matrices. So if we have like this type of vector space, V is of type this. It consists, this is the set of matrices of order m cross n, whose entries from F field. So if we have like this, if we have some matrix like A belongs to m cross n over F. So your A is of type m cross n matrix, whose entries like A11, A12, A1n, and this is A21, A22, A2n and AM1, AM2, AMN. So this is your m cross n order matrix. So this A belongs to what? V. If this is your V, then A belongs to V. So what we have to prove for vector space? We have to prove all the 8 axioms. So one by one we can satisfy all. So if we take some B also from M cross n over F, so these two elements belongs to this, and if we add them for closure property, if we add them, then the matrix entries are added. So if we add them, then A plus B also belongs to B. And if we multiply A with some scalar like A, then this A is multiplied by all the entries. Then A11, this is also a scalar. So we can say that this A belongs to V. So if we take A and B belongs to V, then A plus B belongs to V. And if we take A belongs to some F and capital A belongs to V, then this belongs to B, which means closure property is satisfied. Now similarly we can prove all the other axioms. So you can try this. If there is any doubt, you can comment. So next example is third one, that is Pn plus 1. It consists polynomials of degree n. So here there are polynomials, like if you have fx belongs to Pn plus 1, then your fx is of the form an xn, an minus 1 xn minus 1, and so on, a1x plus a naught. So this is the polynomial of degree n if your an is non-zero, the highest power. So this is your degree. So degree of fx is n here. Now for proving Pn plus 1 as vector space, we can take some fx and gx belongs to Pn plus 1. Then we have to show fx plus gx also belongs to Pn plus 1. And you know that if we add two polynomials, then their addition is also a polynomial. So this can be easily verified. And if we take some a belongs to some scalar belongs to f, and some fx belongs to Pn plus 1, and if we multiply a with fx, so you get a1 xn, an minus 1 xn minus 1, and so on, a1x plus a naught. So this coefficient is also from field, that means this belongs to Pn plus 1. So in this way we can prove all the remaining properties of vector space. Now next example, fourth one. Now there are some examples in which we have to check whether it is a vector space or not. So let's start with one example, that is, let S is this a1 a2 such that a1 a2 belongs to real numbers. This is your S, and what we have to show, check whether S is a vector space or not. So we have to check, that means it can be a vector space or not. So we start with first property, first one, closure. So if we take two elements from S, like if your x and y from S, then your x is of type a1 a2, two tuple vector, and y of b1 b2, and if we add these two, we get a1 plus b1, a2 plus b2. This also belongs to real number, this also belongs to real number. That means x plus y belongs to S. And if we take some alpha scalar from F, or your F is R here, so if we multiply alpha with x, you get alpha a1, alpha a2, and so on, alpha, sorry, this is two length vector, sorry, this is two length, so alpha a1, alpha a2. Alpha a1 also belongs to real number, alpha a2 belongs to real number, that means this belongs to S. So now our two closure properties are satisfied. Now commutative addition. In which we have to show x plus y is same as y plus x. This one. So we can start with left hand side, x plus y. That means a1 plus b1, a2 plus b2. Sorry guys, the addition is defined here. Addition is defined as, in this case, addition you can write here. So addition in this case is defined as a1 a2 plus b1 b2 is equal to a1 plus b1, and this is a2 minus b2. And here multiplication is defined as ca1 a2 is equal to ca1 ca2. These two operations are defined. So now here we start with this commutative addition. So left hand side, x plus y, that is a1 a2 plus b1 b2, that is equal to a1 plus b1, and this is a2 minus b2. This is your left hand side. Now right hand side is y plus x, which is b1 b2 plus a1 a2. So this is what? This is b1 plus a1, and this is b2 minus a2, and you know that these two are not same because a2 b2 are real numbers, so that means left hand side is not equal to right hand side. That means this condition is not verified here. It means S is not a vector space. So in order to prove not a vector space, it is sufficient to prove only one condition. So you can check by using any condition, is it a vector space or not. So now say the next example. This type of examples are very important because here you have to check whether it is a vector space or not. So now next example is like if again S is of type a1 a2 such that these a1 a2 belongs to real numbers, and now addition and multiplication is defined as, this is a1 plus b1 0, and multiplication is defined as c a1 a2 is equal to c a1 and 0. Addition and multiplication is defined by this way. So your C belongs to real number, that means this is your field. So we have to prove all the properties. As you know that this a1 plus b1 belongs to R, this 0 belongs to R, that means this belongs to S, and this belongs to R, 0 belongs to R, that means this belongs to S. So closure property is satisfied here. Now we have to start with commutative addition or some other properties you can check. So let's continue with additive identity. It is directly seen from example that the additive identity property is not verified here. So I am starting with this. Now let's take one element, then a1 plus a2. If we add with 0, additive identity. So this is what by definition put here. In place of b1 is 0 and b2 is 0. So you can write here b1 0 and b2 0. So you get a1 plus 0 0, that is a1 0. So if we add a1 a2 with 0, we get a1 0. But for additive identity it should be equal to what? a1 a2. So this condition is not hold here. So we can directly write S is not a vector space. So in this way you can do any example of vector space. You can do any type of questions based on vector spaces. You can check, you can prove either is it a vector space or not. So these are the main examples of vector space, like standard examples Rn, M cross n, P n plus 1. So these are the standard examples of vector spaces. So thank you guys.